Hello, in this video we're going to talk about intermolecular forces. So intermolecular forces are forces between neutral atoms and molecules, and they mediate interaction between atoms and molecules, how they hold together as a liquid, the energy required to pull them apart to turn them into a gas, things like that. And so here we're talking about neutral atoms as opposed to ions. In chapter 6, we learned about ionic compounds and how they fit together. And that's driven by electrostatics. The positive charge and the negative charge interact together very strongly. And so that strength of interaction is much higher than what we're dealing with here. Here we're just looking at forces between molecules and atoms that are not on the order of a +1 or -1 charge, either a lot less than that from a dipole or even zero charge, and the subtle forces that are at play between atoms or molecules there. So these are also different from intramolecular forces, which is typically a covalent bond between atoms that hold the molecule together. So that force is not what we're talking about here. We're talking about between molecules. So to motivate this, water is a liquid at room temperature. That's great. Hydrogen sulfide, H2S, is a gas at room temperature. Well, if you look on the periodic table, oxygen and sulfur are right above and below each other. So you'd think these might behave more similarly. But they're very different. So here's water, here's hydrogen sulfide. I mean, toxicity concerns aside, why is hydrogen sulfide a gas? Well, this comes from intermolecular forces. Water has greater forces between the molecule that hold it together into a liquid, given some thermal energy, whereas hydrogen sulfide has less forces between the molecules, so given the same thermal energy, the molecules will tend to separate and form a gas as opposed to staying together as a liquid. So intermolecular forces drive a lot of things. Greater forces holding the molecules together leads to higher melting points and higher boiling points. There's a stronger energy holding these things together, so you need more thermal energy to pull them apart, either to allow them to slide past each other as a liquid or to vaporize and turn into a gas. Also, with greater intermolecular forces, it takes more energy, more enthalpy in this case, to vaporize, to take the molecules from being close together as a liquid to far apart as a gas. There's greater surface tension, which we'll talk about in the next video. There's also greater viscosity, which is resistance to flow. Okay, it's also a lower vapor pressure with greater intermolecular forces, which we also talk about in a subsequent video. So one of the things we'll talk about here and how to determine what intermolecular forces are at play is polarity. And so this is a blast from the past in Chem 8, and let's review this because you're going to need to use it in this chapter and you may have forgotten it. So, quick crash course on how to determine if a molecule is polar. So a polar molecule has a net dipole moment. Okay, so first up you got to draw the Lewis structure. Okay, feel free to look back to Chem 8 if you forget how to do that. Then you need to determine the molecular geometry, how these atoms are arranged around the central atom. Then you have to figure out if each bond is polar, and so a polar bond has a difference in electronegativity between the two atoms. A more polar bond has a larger difference in electronegativity between the two atoms. Okay, now if your polar bonds cancel in space, the molecule is nonpolar. If your polar bonds do not cancel, then the molecule is polar. So by way of example, if you have carbon dioxide, the Lewis structure looks like this. Now looking at each one of these bonds, carbon and oxygen have different electronegativities. Carbon has an electronegativity of 2.55. Oxygen has an electronegativity of 3.44. So oxygen being more electronegative, closer to the top right of the periodic table. These bonds are polar, in that the positive end of the polar bond is close to the carbon, the negative end is by the oxygen for each bond, and so we can draw these little arrows like this, with the plus on the rear end of the arrow meaning positive, and the arrow points towards the negative. Now your textbook does have a different convention for drawing arrows, so keep that in mind. They draw them the other direction without the plus on the tail. Okay. Now both of these bonds are polar, but they oppose each other. They point 180 degrees from each other, and they're the same degree of electronegativity difference on both bonds, so the same amount of polarity. So overall, they cancel in space. So that's what I meant by that. Now, let's use another example. So this is formaldehyde. And, okay, when you look at this, it has the same carbon-oxygen bond. Now, the carbon-hydrogen bond is technically not polar. It has a little electronegativity difference. Hydrogen's 2.1, carbon's 2.55. But generally, we say anything under 0.4 of a difference in electronegativity is nonpolar. So we'll ignore those for now. And that's a fairly good assumption. Now, okay, between carbon and oxygen, it's the same story as carbon dioxide on the left, but now nothing opposes it. So this molecule has a net dipole moment. When you add them all together, there is some resultant dipole moment. So we say this molecule is polar. Now, this will have very different outcomes for intermolecular forces, in that carbon dioxide is nonpolar, formaldehyde is polar. So you can shortcut this process of determining polarity and get it right about 85-ish% of the time. So let's talk about that. First of all, up here I have the types of geometries that we cover in Chem 8: linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. And the numbers here are the bond angles. So if you have no lone pairs on the central atom and all the external atoms are the same, then it's nonpolar. Because in all of these shapes, the atoms on the outside will all oppose each other in space. It's a little hard to see for the trigonal bipyramidal one, but it's true there too. But polarity can arise if you have different atoms around the central atom. That's not always true, but it can occur there. It can also occur if you have lone pairs on the central atom. Not always, but often if you have a lone pair on the central atom, that will lead you to something being polar. So, general idea, if you have a lone pair on the central atom, there's a decent chance it's polar. If you don't have a lone pair on the central atom, decent chance it's nonpolar. It's a not perfect shortcut. So you're better off doing the process on the last page. But if you're in a hurry, you can start here and then think about it a little more. Okay, so a little practice question. I'll put the pop-up quiz on this, the pre-quiz as I call it. So consider the molecules carbon disulfide and nitrogen trifluoride. Which one of these is correct? Okay, now we can talk about intermolecular forces. Okay, so ionic forces are on the left here. And remember, this is something that's not really what we're talking about now. Right? Ionic forces, two oppositely charged ions. Van der Waals forces is the umbrella term for intermolecular forces between uncharged atoms or molecules with a net neutral charge. And so all of these molecules have London dispersion forces. And if the molecule is nonpolar, that's the only intermolecular force that's at play, that's operating. Whereas if your molecule is polar, it has London dispersion forces and dipole-dipole forces. And this adds to overall more intermolecular forces than if it did not have a dipole moment. And then there's a special kind of dipole-dipole interaction that's called a hydrogen bond. And that's only for specific cases. Just a particularly strong dipole-dipole interaction that we like to talk about. Okay, so let's talk about each one of these in turn. But before we do that, a little note that individual atoms, such as helium, neon, things like that, they act like a nonpolar molecule in this consideration. Okay, so London dispersion forces. All molecules and atoms have dispersion forces, and they're caused by fluctuations in electron distribution around the atom or molecule, and I'll talk about that in a second. The strength of this dispersion force increases with the size of the electron cloud, so more electrons, the more polarizable the atom is, and the more dispersion forces you can have, or the stronger dispersion force you can have. Now, let's draw a little picture to try to help this make some sense. Say you have a nucleus, ta-da, and then around the nucleus you have some electrons. I'm going to draw them as dots, which is a pretty bad assumption, right? Really, they're more like waves that are present in orbitals, but I'm going to draw them as dots for the moment. Now, okay, I kind of drew them symmetrically distributed around the nucleus. But say, what happens if, for a short period of time, some of these electrons decide, hey, let's all hang out on the left side for now. And this is going to be a really short period of time that we're talking about. Now, this atom has an unbalanced electron distribution. The nucleus is positive, but then the electrons are negative, and there's more electrons on the left side. So we could draw a little dipole like this. Now, this may exist for fractions of a second, picoseconds, that kind of length of time, really short period of time. And then, okay, well, now the electrons decide, hey, let's redistribute a little bit. Now, what if we all want to be, I don't know, let's kind of hang out on the other side. That was fun being over here for now, but let's move over here. All right. And now maybe it's more symmetrical. And then you can kind of go on and on with this, right? So say the electrons decide to be over here. Now you have a dipole moment pointing this direction, so on and so forth. So you can see why the strength of this force increases with the size of the electron cloud. If you have more electrons, you have more ability for this to happen, and it's a stronger force. You can create a stronger dipole. Kind of weird, right? But it works, and it's an effect that we can measure and see. Okay, here's another picture from a textbook that might be better than the one I drew. Say you have over here atom A and atom B, and then there's no polarization to start. So atom A has an instantaneous dipole for a very short period of time. Well, atom B next to it, the electrons are now drawn this way because the negative electrons are drawn towards the partially positive edge of the atom next to it. So then atom B will have an induced dipole to mimic the one for the atom next to it. And the same is true for molecules. So the right side of this is trying to draw two molecules. You can have electron distribution around your whole molecule, have an instantaneous dipole, which will then induce a dipole into the molecule next to it because these electrons say, hey, I want to go that way, and they do. So again, this will increase when you have more electrons. It'll be a stronger effect. But overall, it works for all atoms and molecules. So you can use this kind of logic to look at these different molecules and try to figure out what has the highest boiling point. Okay, if you look at these, hydrogen, fluorine, and chlorine all behave very similarly in Lewis structures. They all like to make one bond to something else. So all four of these are going to be tetrahedral geometries with no lone pairs on the central atom, which means all four of these are nonpolar. So we're not looking at dipole-dipole forces here. But hydrogen has a much smaller electron cloud than fluorine, which has a smaller electron cloud than chlorine, right? Chlorine has the biggest amount of electrons floating around. And so it can create the strongest instantaneous dipole, which will then induce stronger dipoles in molecules next to it, and it'll turn out to have more intermolecular forces. Okay, so this has higher intermolecular forces. For some odd reasons, my arrows always look like garbage. Okay, higher intermolecular forces. Now, how does that relate to boiling point? So at the boiling point, you have thermal energy for how hot you've heated the sample, and that suddenly is enough energy to cause the liquid molecules that are close to each other to fly away from each other as a gas. So if you have stronger forces between your molecules, it takes more thermal energy to pull them apart from each other into a gas. So higher intermolecular forces equals higher boiling point. And that's borne out by looking at the numbers. You look up the boiling points for all of these, and it does follow this trend. Carbon tetrachloride is a liquid at room temperature. Methane is natural gas that you cook with, so that's, of course, a gas at room temperature, and CF4 is still a gas at room temperature. And then if you were to keep going and you went to CBr4, it would presumably have an even higher boiling point. So it's a pretty straightforward example, right? We have a very obvious relationship between our three examples. But you can use this logic on larger and more complicated molecules as well. All right, so now we're on to dipole-dipole forces. So these are attractive forces between polar molecules. And so these are molecules with dipole moments. We just talked about that. So here the positive end of one molecule attracts the negative end of the other. Similarly to how positive ions and negative ions attract each other, but here we have neutral molecules that just have a very slight distribution of charge, positive on one side, negative on the other side. And so these molecules attract each other because the positive and negatives attract. This is stronger than dispersion forces because there's a permanent dipole and not an instantaneous dipole. And then if you have a larger dipole moment, a bigger electronegativity difference, you'll have a greater force holding the molecules together. So on the right over here, we have a picture trying to show that you have a carbon in the middle, and then you have an oxygen on the top, and then hydrogens on either side. We're drawing formaldehyde again. And then here it is drawn just out to the left as a Lewis structure. And so, right, we just drew this molecule. Here's the dipole moment. So that means this over here is partially positive. This over here is partially negative. And if you have another formaldehyde molecule, which this time I'll draw it with the proper geometry, it has the same deal. It's partially positive here, partially negative here, and then the positive and negatives attract. Okay, so that's dipole-dipole forces. Fairly straightforward. If it has a dipole, it has these forces. Now there's one special kind of dipole-dipole force called hydrogen bonding. And this is the strongest intermolecular force of all. And it only occurs in polar molecules that have these very specific bonds: hydrogen-fluorine, hydrogen-oxygen, or hydrogen-nitrogen bond. The reason why these bonds are the ones that form hydrogen bonds is because fluorine is the most electronegative element, so it'll have the largest electronegativity difference with hydrogen. Oxygen is the second largest electronegativity. And then nitrogen is up there in the top 5 for electronegativity. So here's the picture again, where you have the oxygen-hydrogen bond here, and it's partially negative on the top, partially positive on the bottom, the way it's drawn. And so this will attract itself to the oxygen-hydrogen bond here, which the positive end of one molecule is attracted to the negative end of the other molecule, and that forms a hydrogen bond. So here's an example of hydrogen bonding in action. But before we even get to the hydrogen bond part of it, let me bring out something else. So this row right here is all nonpolar, methane, and then you take the carbon and you start going down the column of the periodic table. So all of these are nonpolar, so they have lower boiling points than, say, very comparable molecules above them that are polar. Which that makes sense, because we just said that if it's a nonpolar molecule, it only has dispersion forces. But if it's a polar molecule, it has dispersion forces and dipole-dipole forces. That's overall stronger, and thus stronger intermolecular forces is a higher boiling point. So that part makes sense. But what's unique about hydrogen bonds is this trend. Okay, so if you see this trend kind of going down here, you'd expect NH3 to be over here somewhere, because it's a smaller molecule, so it has less dispersion forces, in addition to its dipole-dipole forces. But due to the uniqueness of the hydrogen bond, it has a much higher boiling point than it would otherwise, because there's greater intermolecular force here. Same is true for HF compared to HCl and HBr. And then the same is true for water. Water with a high boiling point of 100 compared to hydrogen sulfide, which is very similar to water. We showed it at the introduction to this video. But hydrogen sulfide has a much lower boiling point. And since room temperature sits about here, that means that water is a liquid at room temperature because it does not have enough energy to reach its boiling point, whereas hydrogen sulfide is a gas at room temperature because by the time you're up at this higher temperature, you're well above the boiling point of hydrogen sulfide. So I've talked about this already. I'll just leave the slide here, that here are the intermolecular forces down on the bottom of this, and dispersion's the weakest force, dipole-dipole is the next, and then hydrogen bonding is the strongest. So that's what we have on intermolecular forces. Thanks for listening.